Welcome students. In this lecture, we will dive deep into the structure of the atom, one of the most important and fascinating topics in all of chemistry. We're going to journey through time to see how scientists first discovered the atom, what tiny particles it's made of, and explore the different models that have helped us understand what it truly looks like inside. By the end, you'll have a solid foundation for understanding the very building blocks of our universe. So, what exactly is an atom? To put it simply, an atom is the smallest possible particle of an element that still has all the chemical properties of that element. Think about it, everything around us, from the air we breathe to the screen you're watching this on, is made of atoms. They are incredibly, almost unimaginably, small. A single atom is about 1/10,000,000th of a meter across. It's so small that a single drop of water contains billions and billions of them. Believe it or not, the idea of the atom isn't new, it's thousands of years old. Way back in ancient Greece, a philosopher named Democritus was the first to propose that if you keep cutting something in half, you'll eventually reach a tiny, indivisible particle. He called these particles atomos, which means uncuttable. For centuries, this was just an idea, but it laid the groundwork for modern scientists who would later develop detailed, evidence-based atomic models. The first major scientific step forward came in 1803 with John Dalton. He presented the first scientific atomic theory, which completely changed how we thought about matter. Dalton's main points were revolutionary for his time. First, he stated that all matter is made of tiny, indivisible particles called atoms. Second, he proposed that all atoms of the same element are identical in mass and properties. Third, he explained that atoms combine in simple whole number ratios to form compounds. And finally, he declared that atoms cannot be created or destroyed during a chemical reaction, they just get rearranged. His model pictured the atom as a simple, solid sphere, like a tiny billiard ball. For nearly a century, Dalton's indivisible atom was the accepted model. But that all changed in 1897 when J.J. Thomson made a groundbreaking discovery. While experimenting with cathode ray tubes, he found that atoms were not indivisible after all. He discovered that these rays were made of particles that were much smaller than an atom and carried a negative charge. He had discovered the electron. This proved that atoms had smaller components inside them, opening up a whole new world of subatomic physics. With his discovery of the electron, Thomson needed a new model for the atom. He proposed what is famously known as the plum pudding model or the watermelon model. Imagine a watermelon. He suggested that the atom was a sphere of positive charge, like the red flesh of the melon, with negatively charged electrons scattered throughout it, like the seeds. This model was a huge leap forward because it was the first to include both positive and negative charges within the atom. But science never stands still. In 1911, a scientist named Ernest Rutherford decided to test Thomson's model. He designed the famous gold foil experiment, where he shot tiny, positively charged alpha particles at a very thin sheet of gold foil. According to Thomson's model, the particles should have passed straight through. While most of them did, something astonishing happened. Some particles were deflected at large angles, and a few even bounced straight back. This was like firing a cannonball at a piece of tissue paper and having it come back and hit you. Rutherford concluded that the atom must have a tiny, dense, positively charged center, which he named the nucleus. He also realized that most of the atom is just empty space, and the electrons must be moving around this nucleus. Based on his experiment, Rutherford proposed his own nuclear model of the atom. He pictured the atom like a mini solar system, with electrons orbiting the central nucleus, much like planets orbiting the Sun. This model explained why most alpha particles passed through the gold foil. They were traveling through the empty space. It also explained why some bounced back. They had hit the dense, positive nucleus head-on. However, his model had a major flaw. According to classical physics, an orbiting electron should continuously lose energy and spiral into the nucleus, causing the atom to collapse. But we know atoms are stable. This problem was solved in 1913 by Niels Bohr. He took Rutherford's model and improved it by incorporating ideas from the new field of quantum mechanics. Bohr suggested that electrons don't just orbit anywhere. They travel in fixed specific paths or orbits called shells, each with a fixed energy level. He proposed that an electron can stay in its orbit without losing energy. It can only jump to a higher energy level by absorbing a specific amount of energy, or drop to a lower level by releasing energy, often as light. This model successfully explained the stability of atoms and the light spectra emitted by different elements. So, let's summarize the modern view of the atom. It consists of three main subatomic particles. First, we have the electron, which has a negative charge and an extremely small mass. It exists in the space outside the nucleus. Inside the nucleus, we have the proton, which has a positive charge that's equal in magnitude to the electron's negative charge. The proton is much heavier than the electron. Finally, also in the nucleus, is the neutron. As its name suggests, the neutron has no charge. It's neutral. Its mass is almost identical to that of a proton. The nucleus contains almost all the mass of an atom. To identify an atom, we use two important numbers, the atomic number and the mass number. The atomic number, represented by the letter Z, is simply the number of protons in the nucleus. This number is unique to each element and defines what element it is. For example, any atom with 6 protons is a carbon atom. The mass number, represented by the letter A, is the total number of protons and neutrons in the nucleus. For example, a common form of carbon has 6 protons and 6 neutrons, so its mass number is 12. Now, this leads us to an interesting concept called isotopes. Isotopes are atoms of the same element that have the same number of protons but a different number of neutrons. Since they have the same number of protons, they have the same atomic number and are the same element. But because they have different numbers of neutrons, they have different mass numbers. A classic example is carbon. Most carbon atoms are carbon-12 with 6 protons and 6 neutrons. But a small fraction are carbon-14, which has 6 protons and 8 neutrons. They are both carbon, but carbon-14 is heavier. Finally, let's talk about how electrons are arranged. According to Bohr's model, electrons fill up the shells starting from the one closest to the nucleus. These shells are labeled K, L, M, and so on. Each shell can only hold a certain maximum number of electrons. The first shell, the K shell, can hold up to 2 electrons. The second shell, the L shell, can hold up to 8. The third, the M shell, can hold up to 18. Let's take sodium as an example. Sodium has an atomic number of 11, meaning it has 11 electrons. The first 2 electrons go into the K shell. The next 8 fill up the L shell. The last remaining electron goes into the M shell. So its electronic configuration is 281. This arrangement determines an element's chemical properties. So, to recap, today we've journeyed through the history of the atom, from Dalton's solid sphere to Thomson's plum pudding, Rutherford's nuclear model, and finally Bohr's quantum model. We learned about the 3 fundamental subatomic particles: protons, neutrons, and electrons. We also covered key concepts like atomic number, mass number, isotopes, and how electrons are arranged in shells. Understanding the structure of the atom is truly the foundation for all of modern chemistry. Thanks for watching. If you found this lecture helpful, please give it a like and subscribe to the channel for more high-quality chemistry lectures. See you in the next video.